Okay, so hi everyone, welcome back. It's the first seminar of our One Word API series. It's my pleasure having here as our first speaker FX Briol, who is a professor in statistics and machine learning at UCL. FX has also joined the organizer committee of the One Word API, so he will be around with us also in the coming month. And today we'll talk about multi-level neural simulation-based inference. Thanks.
Thanks, Messi. So thank you very much for having me. Also, thank you for inviting me to be an organizer. I should clarify that I did not invite myself. So, so I first got the invitation to be a speaker. So hopefully so I can't see the people that are here. So if you have a question, please write it in the chat and then Messi can interrupt me and tell me. But right now, when I'm sharing my screen, I can't see what people are saying. So what I'm going to do today is I'm going to talk about this paper, which is about to appear at NeurIPS. And this is a paper which is a collaboration mostly with Yuga Hikida, who's a PhD student who's just started at Aalto, where he works with my kind of long-term collaborator, Ayush Bharti, and also with my UCL colleague now, Jeffrey, who's in the Department of Physics here at UCL. Okay, so obviously this is in the seminar series, most people should know what simulation-based inference is, but let me just do a quick recap, mostly so we can kind of recall the notation that I'm going to be using throughout the talk. So here I'm going to have some observed data, which I'm going to call Y. So Y1 to Ym will be the observed data. And I'm going to do Bayesian inference for some parameter of a model, where I'll start with a prior pi of theta and then update with with my likelihood. So here I'm assuming IID data, and I'm interested in this posterior. Right. Now, obviously, the problem in simulation-based inference is that you don't have access to this likelihood. And that can typically be because the model is just too complicated and you can't write down the likelihood. And so what you're trying to do is Bayesian inference, but you don't have access to one of the key quantities. And so you have to find a way to kind of bypass this quantity to still get access to your posterior. So the way that people do this is using what's called a simulator. And there's many ways you can kind of represent a simulator, but for me, a simulator is a pair of a map G theta, which is fully deterministic, and a distribution U, which encodes all of the randomness. So basically, if I pick a value of theta, i.e. a value for the parameter of my model, I can ask my simulator to generate new synthetic data by just simulating from U and applying this map G theta. And so the idea in simulation-based inference is that we're going to bypass evaluations of this likelihood using simulations from our simulator. So we have control on the simulator. Okay. Now, there's two kind of main approaches. I mean, there's more than two, but I'm just sort of like summarizing the key directions in the literature. So one of them is approximate Bayesian computation. And this one has been around for a much longer time. And then more recently, there's been advances in what I call neural-based simulation-based inference, which will be mostly the focus of this talk. So most of my talk will be on these kind of newer methods. Okay, so let me just give some ideas of where you might find simulators. So for example, simulators are used at CERN. So I've just read something about how people are starting to use simulation-based inference for particle physics at CERN. It's been used for a much longer time in neuroscience, in epidemiology, genomics. Recently, I was at a conference in Singapore where someone talking in the same session as me was from Apple, and they were talking about how they're using simulation-based inference within the kind of Apple Watch, the kind of health monitoring in the Apple Watch. And there's this very nice website where you can find out about lots of advances, both on the more applied side and on the more kind of methodology side in these kind of neural-based simulation-based inference methods. Right. So the challenge that we thought about, well, that we were trying to tackle in this paper is that sometimes simulators can be really computationally expensive. Now, I've not really told you what I'm doing with my simulator beyond the fact that I'm kind of using it to generate synthetic data. But typically, regardless of the method I'm going to be using, I'm going to have to do this, many, many times, potentially thousands, hundreds of thousands of times. And that's the reason that if you look at most SBI, so SBI stands for simulation-based inference, and I'll be using this acronym throughout, most papers will typically have simulators which take a few seconds or less to run. And that's because I'm going to need to run my simulator so many times that otherwise, we're just burning trees to generate our papers. Now, even if the simulator starts taking, let's say, a few minutes and you need thousands of simulations, that starts becoming a problem for most people. Now, obviously, you might have access to like a lot of compute resources. Maybe our colleagues at Apple do when they're kind of using this for their Apple Watch. But at least at UCL, they haven't quite given me infinite resources yet. And so you kind of need to do something about this. So trying to do SBI for these more expensive models is definitely a challenge that many people will face. Okay. And so what this means is that there are many applications where people could be using SBIs, but they don't because the simulator is too expensive. Okay. Right. So the motivating kind of application for us comes from physics. It comes from cosmology, to be precise. And it comes from discussion with Niall. So about a year ago, Niall and I had some meeting, and we were discussing how they're using SBI in cosmology, and specifically, he's heavily involved in what's called the dark energy survey. So that's a very large kind of intercontinental collaboration with over 400 scientists in all sorts of countries. And basically, just to summarize, my kind of naive understanding of what's happening is that they're building a huge telescope on top of a mountain in Chile. They take some pictures of the sky. So that's cool. Yeah. So the telescope is this dark energy survey camera. They take some pictures of the sky, which might look something like this. And then based on these pictures, they want to find out lots of things about the evolution of the universe, which is clearly a very ambitious problem. So the sort of things that the dark energy survey is interested in is, for example, the proportion of dark energy. So I'm not an expert in cosmology, so I can't tell you all the kind of finer details of this, but basically they really care about finding this and they want to kind of estimate this very accurately. Okay. Now, what happens in practice is that, well, basically Niall and his colleagues apply for a huge grant to get lots of compute budget, and they then run these really, really big simulations of trying to kind of encode all of the things that we know about evolution of the universe into a big simulator. And then they basically run this simulator, i.e., in my notation, they pick some U's and some thetas and run the simulator. And there's what they call the Gower Street simulation, which is basically a load of these runs from UCL physics. And what they're going to try to do is try to basically get an understanding of, how the universe was generated using these simulations. Now, obviously, that's not exactly what we're going to do, but that was the kind of motivating application for us. In the paper, I'll come back later to this. We have this picture which basically kind of illustrates what is feasible with these sorts of things. So firstly, running one of these really long simulations can take hundreds of hours. So that's a bit of a problem. But if I start taking out some of the physics in my simulator, I can potentially have a simulator which is much, much cheaper, computationally cheaper. And so what happens is that potentially what I could do is I could have, in this case, the right-hand side, which is one picture, or the slightly different picture on the left-hand side, which, maybe I should have used a slightly better way of saving the picture because it's a bit blurry here. But basically, the left-hand side is missing some parts of the physics. It takes a lot less time to generate it, but it's actually quite similar to the right-hand side, which takes a lot more time. So in fact, the right-hand side takes about 100 times more than the left-hand side to generate. Okay, And so here the idea is that actually, this is just one example from cosmology, but all across science, people are used to using different simulators. And very often what they do is they simplify their simulators just to be able to do computation with them, whether it's for SBI or for something else. And here the idea was that to kind of bring some tools from statistics, from in fact Monte Carlo methods, to SBI to try to kind of allow SBI users to make use of these kinds of different fidelity levels when they try to do inference. Okay, now there's lots of existing work on multi-fidelity SBI. And most of it has been in terms of approximate Bayesian computation, which is this kind of class of method that has been around for a bit longer. Now, we didn't focus on this mostly because, at least when I talk to Nao, he's very enthusiastic about these newer methods. And one of the reasons that he's very enthusiastic about them is that they are so-called amortized. So basically, you basically have like a huge cost at the start when you're kind of training your method. But then I can do inference even if I change my data set a bit, or if I change my prior a bit, I can basically get my posterior much, much more quickly with these newer methods. And I'll explain why in a moment when I actually explain what these are. There's been also another attempt that appeared a few months before our paper, so we were already kind of halfway through the paper. So there's this nice paper which basically uses some form of transfer learning techniques to kind of do this, and it's an interesting kind of first step. Our method was kind of trying really to have something which also has theoretical backing, and so that's kind of like the main advantage of our method so far. But it's a kind of interesting alternative here. Okay. So the open problem for us was having something where we can have strong theoretical guarantees on the performance of the method, try to understand how this method depends on the number of simulations from each fidelity level, etc., etc. Okay, so in order for me to kind of explain what we did, I need to explain to you what NeuralSBI is. And I expect that many of you will know this because obviously this seminar series has had quite a few talks on this. So I hope you will indulge with me whilst I explain this again in case some people haven't. So the way I think about NeuralSBI is really as a two-step procedure. So step one is basically use my simulator in a way to create a surrogate of either my likelihood, my posterior, or maybe some other quantity of interest, which will be useful to get a handle on the posterior ultimately. And the way I'm going to do this is I'm going to use my simulator to generate lots and lots of synthetic data for different theta values and use. And to be able to then fit kind of some sort of conditional density model to that synthetic data. Typically, this is done with a conditional density model, which is something like a normalizing flow. It doesn't have to be. And I call this a neural surrogate. Okay, so that's the first part. Now, this part is the usually very expensive part because you're simulating a lot from your simulator. And of course, if the simulator is expensive, this is going to take you a lot of time. The second part is basically once you've got your surrogate, you're just using it to do Bayesian inference with the actually observed data. So not the synthetic data, but the observed data. Yeah, so the advantage of doing that is that now you've spent all this time training a good surrogate and you can actually do Bayes because you didn't have your likelihood before, but now you've got a surrogate for it. And so you can use Bayes and kind of approximate the posterior with standard techniques like MCMC or variational inference or whatever your favorite technique is to approximate posteriors. And so for those of you that want to find out more about this, there's these two review papers that I've put here. They're both from this year and both very nice and kind of complementary ways of seeing what these NeuralSBI methods do. Okay, so in order to explain kind of this first part, so this kind of neural surrogate, I need to explain to you what a normalizing flow is, because that's the main neural surrogate that we'll be using. So obviously, if you're a statistician, you've probably even taught this, so how to deal with change of variables, or how to use transformations of variables in deriving their density. So basically, normalizing flows, they use these kinds of tools, but they take it a bit to the extreme. So we all know this thing, so we can obtain the density of x if we know that x is t of v, where we know the density of v using the following formula. And now the idea is, okay, well, we have this new density. Maybe if we make t very flexible, and v to be some sort of simple distribution, we might be able to have actually quite a flexible density model, okay? And obviously, since, well, there's some connections with machine learning, we're going to have to start using neural networks to do so. So the way we're going to do is we're going to build this map as the composition of simpler maps. Each of these maps will be parameterized somehow. In fact, these parameters will typically be the weights and biases of some neural network. And so now we have what's basically a normalizing flow. Now, obviously, I'm kind of generalizing here. So, this is the kind of general view of what a normalizing flow is. There's lots of subtleties and like things you need to think about to keep things tractable. But the key thing is that we're going to use a composition of simpler maps to get a very, very flexible density model. So here I'm calling it Q-phi. And again, so there's these two review papers that you can have a look at if you're interested in normalizing flows. Now, in our case, what we're going to do is we're going to create a surrogate not of a marginal density, but a conditional density. What we're trying to approximate is a likelihood, i.e. x given parameters. And so what we're going to do is we're simply just going to parameterize this neural network, also not just with phi, but with theta, and suddenly we have a conditional density model. Okay. And so the whole game is how to pick these maps in a way to keep this density tractable. So the key thing for normalizing flow is you have a tractable density, but that is very, very flexible. Okay, so I borrowed these plots from this review paper from a few years ago, which kind of explains the concept. So imagine you have this kind of fairly simple distribution at the start that looks like a Gaussian. What I can do is I can apply simple transformations several times, and then I can start having much more kind of flexible distributions. And that's basically the intuition you should have in your head when you think about normalizing flows. Okay. Okay, so let me just summarize what I said. So what I said is we're going to look at neural SBI methods. And neural SBI methods, they are a two-step procedure. First step is you you simulate lots of data from your simulator and fit a normalizing flow, for example. And then step two is you use this surrogate to do Bayes. Okay, so there's different methods that fall into this category, but probably one of the most well-known one is neural likelihood estimation, which I'll now explain in a little bit more detail. So let me again go through these steps, these two steps, but now adding a bit more mathematical detail. So step one, you have this Q-phi, which is my normalizing flow. And it's basically a surrogate of, the density that's used in my likelihood. So what I've done is I've simulated from the prior to get some theta values. And for each of these theta values, I've used my simulator to get some x's. So I've got a lot of that. And now what I'm going to do is I'm going to fit my normalizing flow, i.e. I'm going to find some good phi values, some good parameter values for that normalizing flow using some objective. And typically, but not always, it's the negative expected log density. So what I'm trying to really approximate is the thing here on the right-hand side. But obviously, these expectations are intractable, and all I'm doing is approximating them with the data that I have. So what I'm doing is I'm actually finding phi that minimizes the left-hand side. Okay, So that's neural likelihood estimation. This is obviously like the expensive part. So you need a lot of samples for the left-hand side to be a good approximation of the right-hand side. And obviously this can be also quite a difficult thing to do because the normalizing flow, although the density is tractable, you're still training a neural network which has all sorts of subtleties attached to it, which is kind of the difficult bit. Okay. Now, once you've done this, you've found a good estimate for phi, which I phi hat n. What I can do is I can just go and do Bayes. I get an approximate posterior, which I obtain by starting with the same prior I was going to use. But instead of updating with my likelihood, which I don't have because we're doing SBI, I'm using my surrogate of the likelihood with this normalizing flow that I've trained at step 1. And so now I'm getting this posterior. I'll call it the NLE posterior. And again, now because I have a tractable Q phi, I can go and approximate the NLE posterior whichever way I want. So I can use MCMC, I can use variational inference, whatever I want. Okay, and so this general approach is what's typically referred to as neural likelihood estimation. Okay, now for us, the kind of key step will be this first step, because this first step is what's really expensive, and it's the step that really involves the simulator. Once I've done step 1, I don't need my simulator anymore. I just need my observed data and my normalizing flow. Okay, so yeah, so you can do this for the likelihood. You can do this, for example, straight away for the posterior. And I'm not really going to talk about this due to lack of time, but you could have an equivalent method called neural posterior estimation and various other extensions. Okay, so the question really that we asked is, can we do this slightly better? Now, I'm someone that's worked quite a bit in Monte Carlo methods before. And so to me, well, when I see something like this, I'm thinking, okay, well, this is a standard Monte Carlo estimator. We know that there's lots and lots of more fancy Monte Carlo methods we could use. Why not try some of them? And this is basically what we did in this project. So the specific type of method we used is what's called multi-level Monte Carlo. And this is a method that's been used really extensively in applied mathematics and uncertainty quantification, mostly because having kind of different levels of fidelity is very natural when you have to deal with things like PDEs, ODEs, SDEs, where, for example, you could have like a discretization level, which leads you to approximate solutions. So certainly multi-level Monte Carlo is very popular in kind of the Monte Carlo literature. It has been for over 10 years. It's been around for much longer, but it hasn't yet been used, well, until now, for these neural SBI methods. And so what we thought was, okay, well, let's try to make this work in this setting. Okay, so since I don't really want to assume that everyone here knows what multi-level Monte Carlo is, let me try to recap what it does. So here you can basically forget about all of my notation from before, and we're going to start with a very simple problem. So the problem is that of approximating this expectation of f against some distribution mu. Now, the setting is a little bit more complicated because instead of just having my function f, I'm actually going to have a sequence of functions, f0 to f big L, where f0 is very cheap, but the higher up I go up the sequence, the more expensive the function is going to be when I try to evaluate it pointwise. Now, okay, so my functions get more and more expensive, but they also get more and more accurate. So f0 isn't that accurate, f1 is slightly more accurate, etc., as approximation of f, which is the last element of that sequence. Okay, so that's the setting for multi-level Monte Carlo. And so the idea is, yes, of course, we could just try to do a Monte Carlo estimator of this expectation, but maybe we can use this structure of the sequence to get a better estimator. So one thing I could do is I can just use my notation. So I've defined f big L to be exactly f, so that's what I use. And then what I can do is I can start using linearity of expectations and grouping terms slightly differently. So now what I've done is I've added and subtracted fl minus 1. So I've kept one of the FL-1 in the same expectation as FL, and the other one's been put at the front. Okay, so that's just linearity of expectations. Now, obviously, I have not just FL-1, but I have all the other ones. So I can start adding them, and I get what's called the telescoping sum. So now I've written the fact that my one expectation that I care about at the top left is exactly the same as the sum of L+1 expectations, which is what I have written now. And the idea with multi-level Monte Carlo is to then go and do a Monte Carlo estimator of each of these L+1 expectations. Now, in terms of doing this, so when the first time you see multi-level Monte Carlo, you might think I'm a little bit crazy. Like, I start with one expectation and I would like to approximate it. And instead, I'm making my life harder by turning it into L+1 expectations that I'm each trying to approximate. And that's obviously like a bit weird at first. But the key thing is that here, these L+1 expectations will be a lot easier to approximate than the original expectation. And so actually, it can be, depending on what properties these different functions have, much more beneficial to do this than to do the original problem. So let's think this through a little bit. So the first expectation, this one, so the good thing about this is that it's an expectation of f0, which, as I said, is the cheap function. So potentially what I can do is I can take n0 to be very, very large and get a very good estimate of f0. And that's just because it's cheap, much cheaper than f, my original function. Okay, so that's good. So because I can take n0 to be very large, I'm going to get a pretty decent approximation of this expectation. Now, these terms, the thing that's interesting about them is that it's always differences of two consecutive functions. And since they're all approximations of the function f, consecutive approximations will tend to be actually quite similar. And so you can think of FL minus FL-1 as actually being very close to zero, morally zero. It's not exactly zero because obviously it's just a difference between the different level of approximations, but certainly it's going to be a very small quantity. And as a result, it's going to be a lot easier to estimate it. So if you're estimating a teeny tiny number, even if you're making a bit of an error, your error isn't going to be that large because they're teeny tiny numbers. And so here, what happens is that I can use much fewer simulations to try to estimate these expectations, mostly because they're all kind of teeny tiny numbers. And that's a great thing because obviously the higher up I go through my telescoping sum, the more expensive these terms become. And so the more important it is that I evaluate them as rarely as possible. Okay, so that's the general idea of multi-level Monte Carlo. Now, if I go back to neural likelihood estimation, so I kind of remind you that I kind of told you that this is an approximation of this quantity. So we're trying to approximate this expectation using simulations. So what I can do is I can rewrite this expectation using my change of measure with the generator. So this deterministic part of the simulator. If I have multiple simulators, i.e. multiple generators, I can just rewrite this as the most expensive of the simulators. And then now I just have a joint expectation in theta and u of this quantity, which I'll just call FL. Okay, so now if I have different levels of fidelity, I could define similarly f small l as basically this quantity with a slightly different generator, maybe more approximate. Okay. And so really here, it should become very obvious that it's pretty much direct to apply multi-level Monte Carlo. Okay, so let me just summarize what multi-level neural SBI does. So that's the method that we propose. So we have some data, which has some thetas, some u's, and then some evaluations of the generators. And then instead of doing a Monte Carlo estimator of the objective we're trying to minimize, we're going to use a multi-level Monte Carlo estimator, which is as follows. Now, one key thing which is very important, and this is one limitation of the method that we've developed, is that you need to do seed matching. I need to evaluate consecutive generators on the same thetas and u's. And this is really important for the multi-level Monte Carlo method to actually work well. And if I don't do this, then actually it's not clear that I'm going to get a very good estimator. So this bit is definitely key. And it's definitely a limitation because you don't always fully control thetas and u's, or at least the dependence of thetas and u's on, how the generators depend on theta and u and whether it's in the same way. So it happened to work for all the examples that we've got in the paper, but it's something to kind of keep in mind. Okay, so just to see why the seed matching is important, let's just have a look at the variance of that very last term in the objective. So that last term, it basically depends on the difference between FL and FL minus 1. So if I look at the variance of that, I know that it's the sum of the variances of the individual functions minus twice the covariance of them. Now, if I have seed matching, basically this covariance will be very large because GL and GL minus 1 will be very similar, and therefore FL and FL minus 1 will be very similar. And what this means is that the variance will be very small because this minus 2 covariance term, which is very large, completely reduces the impact of the first two terms. And that's really another way of thinking about why multi-level Monte Carlo works quite well in this setting. Okay. Now, as a Monte Carlo researcher, I basically thought, okay, well, we've got this Monte Carlo objective, we've got this more fancy way of computing expectations. Let's have a, let's just apply it here and it'll be our job done. And it turns out that it wasn't quite the case. So there were some challenges that we faced in terms of training, which means that I should spend more time playing with neural networks than I do. But let me try to highlight what happens. So basically, if I look at this objective, here I've just got 2 levels of fidelity. Once I'm going to start doing optimization of this objective, I'm going to start looking at gradients of it, right? So the first part will give me a term which looks like the expected gradient of F0, whereas the very last bit will look exactly like negative that expected gradient of F0. And so basically, there'll be what maybe I can call informally contradictory gradients, meaning that basically the first part pushes one direction and the last part pushes the other direction. Now, that wouldn't be a problem if both N0 and N1 were very, very large, right? Because if N0 and N1 were very, very large, we'd basically be back to using pretty much the expectation. And so the 2 terms would actually cancel each other, right? And that's actually, the whole point of these telescoping sums is that the terms cancel each other. Now, here what happened is that, N0 might be very large, but N1 is going to be very small. And so actually you might have a lot of variance on that second part. And so what would happen with the training is that, we do gradient descent or some sort of fancy version of gradient descent. Things would go down and then suddenly they would start going up again, mostly because one of the term would push us in the wrong direction because of this variance. And so Yuga had to use a number of tricks to kind of stabilize training, such as renormalizing different parts of the objective to try to stabilize convergence of our method. And this is something that Yuga should take credit for because I didn't contribute very much in terms of that part of the paper. Okay, so the part that I was quite excited about is the fact that we could say something theoretically about the performance of our method. And so here I'm going to talk about what we can say about the variance in the estimator of the objective. Now, when we submitted the paper, some reviewers pointed out that sometimes what you might care about is also the gradient of that objective, given that that's, if you're going to do gradient descent, or some form of advanced gradient descent, you might want to care about the gradient rather than the actual objective. So we've now added that to the paper, but just for simplicity, I've just kept it with the objective here. So under some mild assumptions, what can happen is you get an objective, you get a bound which looks like this. So let me sort of break it down for you. So the first part is that obviously it depends on n0, n1, all the way to n big L, which is the number of samples per level. Okay. It also depends on the norm of G0 all the way to G big L, which is basically measuring the complexity of the simulator. Now, what this bound says is it doesn't say anything yet about how I should choose my number of samples per level or anything like that. It just says, imagine you have a fixed number of samples per level, you have some fixed sequence of generators, what's the error you're going to get in terms of what's the variance you're going to get? Now, in practice, typically, N0 will be quite large because the cheaper generator is cheap, and so we can use it a lot more often. And so this first term you can make small by taking it 0 to be large. And that's basically how you drive the first term to 0 in practice. For the higher up terms, you have these NL terms. That's the number of samples at higher levels. Typically, you can't take that to be very large because, well, your generators higher up the sequence will be more expensive, and so you can't use them as often. Now, the nice thing is that this is counterbalanced by the other part of the bound in each of the terms, which is this norms of the generators. So for the first term, remember N0 is large, so we can make things small. But typically G0, its norm will be fairly large. And the reason is that what we're hoping is that our low fidelity simulators are like pretty decent approximations of the high fidelity ones. But there's nothing to say that they'll be like nice and easy functions to kind of estimate with a Monte Carlo. So potentially this could be fairly large, but it's counterbalanced by the fact that N0 is large. On the other hand, if I look on the other side of the, maybe I can, if I can use, yeah, hopefully people can see my mouse. So if I look on the other term here, what's happening is that I have the norm of a difference. And so basically what this is saying is potentially this term could be very, very small if consecutive generators are actually quite similar. Okay, and so this basically explains why this method can work and when it can work in practice. So it will certainly not work if your sequence of approximations are actually very different from one another, because otherwise this term is very large. But if the sequence of generators, you know, they're all kind of approximations of one another, this method can work pretty well. The last thing I should mention is that there's these constants K, and these are just constants that for the bound that we don't get like a very good handle on. We can track them, but they're probably not very tight. The other thing is that these constants, they depend on phi, phi being the current parameters of your neural network. So these constants can vary with phi. So they vary along the trajectory of the gradient descent. Okay. Now, one thing that I was quite happy about is that to get this bound, you don't need very strong assumptions on anything really. So firstly, for the generator, we basically need it to be smooth enough. So we need to have at least one derivative and 4 moments, which, you know, is a limitation, but isn't like a very crazy request. So a lot of these simulators can be smooth. And this is basically to ensure that, you know, consecutive simulators are actually going to be similar. In terms of what we assume on pi, which is the prior, and u, which is the base measure of my simulator, we just assume that they can satisfy what's called a Poincare inequality. So it's the sort of thing that you would expect to hold for Gaussian uniforms and various other fairly simple distributions. And so obviously, like, satisfying a Poincare inequality is quite a strong condition. But here we're assuming it on the prior, which in any case, in most applications, is something like a Gaussian, a uniform, or some other simple distribution. And on the base measure, which very often is basically a uniform. So this condition is, again, not very strong. And finally, we need some condition on Q phi, which is, for example, a normalizing flow. So we needed to have some form of Lipschitz gradients only locally, and for this Lipschitz gradient not to blow up too fast. And so this condition is harder to check in practice because it depends on your normalizing flow, and there's less study of kind of theoretical properties of these normalizing flows. In the paper, we have a bunch of references where people talk about this, and so you can find out for some normalizing flows it will hold, for others maybe not. Okay. So now I've used my mouse, I can't change. Okay. Now, one thing you can do with multi-level Monte Carlo is you can use basically the bound from here. And you can say, okay, given this bound, how should I choose N0, N1, N2, all the way to N big L, so as to make this bound as small as possible? And this is what we did. And you get something like this, which I think is actually quite good in terms of giving you intuition on how you should use the method. So let's assume that I have a fixed computational budget, C budget, which tells me how many times, or what's the total cost I'm happy to incur with my simulations. So the optimal way of allocating budget is with the following formulas. And it's fairly intuitive. So firstly, let's look at N0 first, so this term. If my mouse wants to come back. Okay, this term. So basically this is saying if G0 is very complicated, well, I need N0 to be larger. And that's kind of fairly intuitive. We know how much larger because of exactly the way in which this depends on G0. On the other hand, here we also know that if consecutive generators are very different, then we also need this number to be larger. But actually, if they're quite small, you can make this number much smaller. Now, the other thing is that the number of times you evaluate N0 will depend on, well, the cost of simulating at C0. So if it's really cheap to simulate at C0, potentially you can simulate a lot more often. But on the other hand, if it's expensive, then you're going to try to simulate less often at N0. And you can get exactly the same thing here for the other levels. Now here it's like a sum of two things, because at level L, we're evaluating both GL and GL plus 1. In fact, maybe I've got a typo, it should be -1. Okay. And obviously this is all proportional to the total budget. Now, I think these kind of expressions, they're quite useful in terms of intuition, but we don't, well, at least we haven't used them in the paper to kind of decide how to allocate budgets. And the reason is that there's this constant of proportionality, which is basically hiding my k's, i.e. my constants from the previous slides. And these k's depend on phi, which will vary through time. So it's not super clear exactly, a priori how I should fix N0 all the way to N big L. But still, it gives me some intuition in how I should scale things if I do have some opportunity to do so. One thing that multi-level Monte Carlo people do a lot is they basically kind of do some initial simulations, and then based on that, they try to estimate these various quantities that are needed for this, for these formulas, and then they sort of adaptively add more in some levels. So we could do something like that, but we just haven't done it. There's also many applications where you don't actually control what the number of simulations is per level. So that's, for example, the case for the cosmology example. Okay. So let me do a couple of examples. I see I'm sort of running out of time, so I should probably hurry up a little bit. Okay, so let me summarize. So what we've done so far is we care about simulation-based inference. We're using these neural methods, and we've discussed how you can kind of think of them as a two-step procedure, where the first step is very expensive because you do a lot of simulations from your model, and potentially could be made much cheaper if you use a slightly more advanced method like multi-level Monte Carlo. And this is what we did. and we've got some nice theory to kind of show why this is sensible. So here's a bunch of applications. So this first example is a very contrived example. It's not something that you would actually face in practice, but it's an example with the G&K distribution, which is one of these distributions that you see in most SBI papers. And the reason you see it in most SBI papers is that it's very simple one-dimensional distribution. Well, sorry, it's one-dimensional, so you can plot it. But it's not that simple. It has these 4 parameters, θ1 to θ4, which actually make it a very, very flexible density for one dimension. And it's therefore not that easy to fit. And you also don't have access to the density. So here what we did is we took this distribution because we know people like it. And I'm, again, not getting my mouse. Sorry about that. But you can see on the top right corner of the screen that I've got Z1 and Z0. So usually people use Z1. That's what the G&K is. And what we did is we kind of manufactured a low fidelity version by adding Z0, which is a Taylor approximation of Z1. Okay, and so this was just a contrived example to kind of see what happens. So let's have a look at the left-hand side. So this is the performance of our neural likelihood estimation method. So this plot, and I should really have the legend for it. So in blue is only high fidelity simulations. And you can see that the performance of the method, so you would want this number to be as small as possible, is good, but not that good. And that's mostly because, we're assuming that you can't have that many high fidelity simulations because they're expensive. And so we're here using only 300 simulations. Now, for this example, we've also given standard NLE 10,000 low fidelity simulations. And actually, it's even doing a little bit better than high fidelity. And the reason is purely because we have so many more simulations. And the Taylor approximation isn't that bad. So actually, it's not that bad an approximation, and therefore we're doing slightly better. And so what we can see is that if we were to enhance these very large number of low fidelity simulations with some high fidelity samples, which is what we do with our multi-level version, you can drive this performance up quite a bit, or you drive this error down, basically by combining both low fidelity and high fidelity. So if you want to see just a picture of what's happening, so the dotted black line here is basically the density from this G&K. Now I said that we don't have access to the density. This is true, but we can approximate it very, very efficiently, which is also one of the reasons that people like to play around with it. And so this is what the black dotted line does. And so you can see exactly what's happening in the previous plots. So basically, in blue is standard NLE with only high fidelity data. And you can see that basically it doesn't have enough data to kind of fit that peak. Low fidelity does a little bit better in green. And basically our method in red does even better by really capturing that peak. Okay. I'm sort of running out of time, so I'm going to skip this one. But basically, similar conclusions hold if I was to use NP, which is the method where you do a surrogate of the posterior. Now, the other thing you could do is you could look at a slightly more advanced model. So this is a model called the toggle switch model. It's also very often used in SBI papers. So basically, it's a model of the interaction of genes through time. So you have something like this, where here I have just a measurement of one gene. And what I've done, if I can pull it, well, it's up. So what we've done is basically there's a difference equation that controls this evolution. And you have a time parameter, which basically tells you something about discretization of this equation. So you can either take it to not be that large, which is what's happening at the top. And that's what I'm using as my low fidelity. Or I could take it to be much larger, which is what's happening at the bottom. And you can tell that it takes a lot longer to get a full simulation of this simulator. So in this example, we use the version of the model where you only just observe what happens for one of the genes at the end of the time interval. And there's 7 parameters to fit, but the observation is only one-dimensional. And so you can see there's low fidelity versus high fidelity. Okay. Now, in this example, if I just plot the distribution at the end, this is what I get. And basically what you can see is that there's basically a bimodal distribution at the end. So let's, for example, look at the green histogram. So the green histogram is what happens if I have a low fidelity simulator. I discretize quite heavily, sorry, not that heavily, my time. What I get is like a peak around 400 and then another peak around 700. Now, if I increase for this particular parameterization of the model, T, i.e. the amount of discretization that I do, I basically get these other colors, either yellow or purple, which basically shift the mode of the second part a bit to the right. And so you can see here that actually, the first mode stays pretty much the same regardless of like the discretization, but we're shifting things a little bit by increasing fidelity. And so here you can imagine that using lots of low fidelity data at least allows you to get a good handle on the first mode, whereas perhaps using higher fidelity data is only needed to get that second mode a bit more accurately. And so here you can see why having multiple levels of fidelity could be helpful. And we see this also in the results. So the kind of metric is the maximum mean discrepancy, and you can see that using for a fixed computational budget, using a combination of all three levels of fidelity gives a better performance than using only high fidelity or only or only medium fidelity or only low fidelity, which are the right three box plots. Okay, I'm very low on time. So the last thing I would say is just that basically this also works for the cosmology example. So we get slightly better performance and we also get slightly better coverage. Now, I should say that this cosmology example comes from, I don't have it here, I had it earlier. We only use some kind of simulations from a package that's been made available for statisticians and machine learners to play around with. So we didn't actually use the kind of real simulations from the Gallus Street people. This is something which I think could be really cool to do. And in fact, so there's been a lot of interest, I think, from the physics community. So ever since we've put our paper on, or since this initial work came out, there's been a number of papers that actually look at doing this for kind of much more realistic cosmological problems. So the kind of summary is that I think there's lots and lots of interesting things to do at this intersection of kind of simulation-based inference and multi-fidelity models. This is kind of evident from that first paper that appeared a few months before ours, our paper, and now all of this interest from practitioners. And so hopefully our kind of contribution is an interesting contribution that where you can have some form of theoretical guarantees on the performance of the method. If you're interested in kind of SBI more broadly, which I assume you are given you're here, I gave a course on this at the Greek Stochastics conference a few months ago, and you can find the slides here or on my website. And also I should mention that my collaborator Ayush gave another related talk at this seminar series back in April, where he talked about an earlier paper which also tried to tackle the cost of simulators in SBI, but mostly focused on the problem that for some simulators, evaluating G theta, the cost of that depends on the value of theta. And so this is like, oh no, that hasn't worked. Okay. We'll have to skip the the little video, but basically this is an example of an application that Ayush has worked on ever since he was doing a PhD in telecommunications engineering, where it's a model of signals being sent from antennas to each other, sorry, from one antenna to another. And there basically there's various parameters which impact the cost and make it like either much cheaper or much more expensive to do a simulation depending on theta. And so we proposed a method that can deal with this in that paper. And so if you're interested, you can always have a look at the recording. Probably conclude on the previous slide, which was my conclusions. Oh, okay, we can get the little video anyway. Okay, that's it.
Okay, thanks a lot. Thanks, that's a very interesting talk. I like to open the floor for any question, and while doing that, I will also stop the recording.